Welcome to today's session. Today let's start with a problem based on the magnetic field at an axial point of a current carrying circular loop. Okay, so example 4.6. A straight wire carrying a current of 12 ampere is bent into a semicircular arc of radius 2 centimeter as shown in figure. Consider the magnetic field B at the center of the arc. What is the magnetic field due to the straight segment? And second question, in what way the contribution to B from the semicircle differs from that of a circular loop, and in what way does it resemble? Would your answer be different if the wire were bent into a semicircular arc of the same radius but in the opposite way as shown in figure? So the answer to the first question, we are asked to find the contribution towards the magnetic field at the center. So at the center of the circular loop, we need to find the magnetic field due to the straight portion. That means due to these straight segments, what will be the magnetic field at the point which is at the center. So when we find or when we use Biot-Savart law, we know we have a term I into dl cross r. Okay, IDL cross R. So here IDL comes along this direction and R along in the same direction. So the angle between IDL and R will be 0 degree. The angle between IDL and R will be 0 degree. So when we apply this Biot-Savart law, IDL cross R is IDL sine 0. Sine 0 is 0. So that magnetic field B becomes 0. So the contribution by the straight portion at the center of the circular loop will be equal to 0. Okay. Now coming to the second part, in what way the contribution to B from the semicircle differs from that of a circular loop? What way contribution to B from the semicircle it differs, and how does it resemble? So if you have a full circle, you know the magnetic field at the center, we derived already the expression, that is mu 0 I by 2r. That's what we discussed earlier. Okay, mu 0 I by 2r, where r is the radius. Now if it is a semicircle, instead of full circle you have a semicircle. So due to symmetry, we can say that the magnetic field will be only half of the earlier one. That means mu 0 I by instead of 2r we have 4r. So the magnetic field, the difference is the magnetic field due to semicircle will be half that of full circle. And what is the resemblance? The direction. Okay, so direction we are using what right hand rule. So we will get, in this case we will get the magnetic field to be into the plane by using right hand rule. Curl the fingers in the direction of current, so magnetic field will be into the plane. Okay, so that is the resemblance. So magnetic field direction is the resemblance and magnitude will be different. Now, would your answer be different if the wire were bent into semicircular arc of same radius but in the opposite way? So here it is in the opposite way. So by applying, so magnitude of the magnetic field will be the same, but direction will be opposite. Here also you can use the right hand rule. So the magnetic field will be directed outward. So dot you have to show for the magnetic field. So direction will be opposite, but the magnitude of magnetic field will be different. Means will be same. Now example 4.7. This is a simple question. Consider a tightly wound 100-turn coil of radius 10 centimeter carrying a current of 1 ampere. What is the magnitude of magnetic field at the center of the coil? So direct application question, you have n turns. So there is slight difference in the form of the equation which you learned. This is the equation. So you learned in terms of small letter n and a. Small letter n is the number of turns and small letter a stands for the radius. So in whatever form you use, the answer remains the same. So by substituting, we will get the answer 6.28 into 10 raised to minus 4 Tesla. Now coming to the next topic, that is Ampere's Circuital Law. Ampere Circuital Law is just like Gauss's law in electrostatics. We know Gauss's law can be used to find electric field due to different continuous charge distribution, where we cannot use Coulomb's law. Okay, so in the same way, just like that means in magnetostatics, instead of Biot-Savart law, we can use Ampere Circuital Law in simple form in many situations. That's the role of Ampere Circuital Law in magnetism. Okay, so Biot-Savart law takes the place of Coulomb's law, and Ampere Circuital Law takes the place of Gauss's law in electrostatics. Okay, so to state the law, we have an open surface with a closed boundary. You can see the open surface with a closed boundary. What is the difference between open surface and a closed surface? See, the surface of a cricket ball is a closed surface. The surface of a cricket ball is a closed surface, and the surface of a lid of water bottle, you just consider lid of water bottle, that surface is an open surface. It is not closed surface, it is an open surface. So just like that lid of water bottle, here we have a surface. Okay, so that is an open surface with a closed boundary. That boundary is closed. Okay, so along the open surface with a closed boundary, we can state closed integral b dot dl is equal to mu 0 I. So closed integral b dot dl is equal to mu 0 I. Closed integral means along that closed surface, sum of all b dot dl. That's what we mean by closed integral b dot dl. That is equal to mu 0 I, where B is the magnetic field. So B is the magnetic field around the closed boundary, and I is the current through the surface, and mu 0 is the permeability of free space. So this is what Ampere Circuital Law is. So in the case of an open surface with the closed boundary, closed integral B dot dl is equal to mu 0 I, where B is the magnetic field along the boundary, and I is the current through the surface, and mu 0 is the permeability of free space. Okay, so while stating the law, you have to draw this diagram also, then only it will be clear. Okay, so this is how Ampere Circuital Law is stated. You can state like this also, that is Ampere's Circuital Law states that the line integral of the magnetic field B around any closed circuit is equal to mu 0 times the total current threading or passing through this closed circuit. So it becomes closed integral B dot dl is equal to mu 0 I. Okay, so in any form you can state the general form of Ampere Circuital Law. So this is called as the general form of Ampere's Circuital Law, because another simple form is there, but this is the general form stated by Ampere. Okay, now coming to the simple version of the Ampere Circuital Law, in that we assume only a closed path, closed loop only we will consider. That means in the beginning we considered an open surface, and as a part of the open surface we had a closed boundary. In using Ampere Circuital Law in simple form, we consider only a loop, a closed loop, not as a part of a surface. So we are not considering the surface, only a loop is considered. Okay, and that loop is called as Amperian loop. Just like we used the term Gaussian surface in electrostatics, here we use the term Amperian loop. Okay, so if we consider such an Amperian loop, then how the Amperian loop should be? So along that Amperian loop, B is tangential to the loop and is non-zero constant, or B is normal to the loop, or B vanishes. So the simple version of Ampere Circuital Law is applicable in these three cases. That means when we consider that Amperian loop, either B is tangential to the loop and is a non-zero constant, and B is normal to the loop, or B vanishes. Okay. Now, if L is the length of the loop for which B is tangential, and let IE be the current enclosed by the loop, then the equation reduces to BL is equal to mu 0 I. So this is actually the simple version of Ampere's circuital law. BL is equal to mu 0 IE, where L is the length of the Amperian loop and IE is the current enclosed by the loop. For example, if you have a current carrying wire like this, suppose current is going like this, and there is an Amperian loop. We considered an Amperian loop like this, perpendicular to the wire, okay, like this, so that the current enclosed here, what it will be, current enclosed by the loop. Current enclosed by the loop, here it is the same as current through the wire, because the loop encloses that wire. Okay, so the current enclosed by the loop, that is IE. Here that is the same as current through the loop. If we take it as I, that is I. Okay, so BL is equal to mu 0 IE, and it is applicable in the three states or three conditions we stated above. Now, application of Ampere's law to a straight conductor. So that is the first application of Ampere's circuital law. So the figure shows a circular loop of radius r. So radius r, and it is around an infinitely long straight wire carrying current. So with this, what we are finding is this: you have an infinitely long straight wire carrying a current I. And at a distance r from the wire, what is the magnetic field? That's what we are finding. Okay, so to find the magnetic field at a point at a distance r from the wire, we need to consider Amperian loop first. So to apply Ampere circuital law, the first step is to consider an Amperian loop. So here we find we use the Amperian loop which is circular. So we have assumed a circular loop of radius r. That is what that circular loop. Okay, that circular loop is the Amperian loop. Okay, so why we chose the circular loop, because it is clear from many experiments. That means starting from Ørsted's experiment, we have seen that those iron filings sprinkled around the current carrying wire, they were aligned in circular shapes, which shows that the magnetic field is circular in direction. Okay, so that's why we assumed this circular magnetic field or a circular Amperian loop. So using the simple form of Ampere circuital law, we have BL is equal to mu 0 IE. Here L is the length of the Amperian loop. Here, since we assumed circular Amperian loop, length of the loop means its perimeter. So its perimeter is 2 pi r. So B into 2 pi r is equal to mu 0 I. Here IE is the current enclosed by the Amperian loop. Here the current enclosed by the Amperian loop, as you can see from the diagram, it is what that current I through the wire. So IE is equal to I. So we have B is equal to mu 0 I divided by 2 pi r. This is very important equation. This gives the magnitude of magnetic field around a straight current carrying conductor. So B is equal to mu 0 I by 2 pi r. So we can state that the magnetic field is directly proportional to current and inversely proportional to the distance. So as we go away from the wire, the magnitude of magnetic field decreases. Okay. Likewise, it varies directly with current. As the current increases, magnetic field increases. As the current decreases, the magnetic field decreases. Now we can see that at every point on the circle of radius r with the wire along the axis, the magnetic field will have the same magnitude at all points which are at a distance r. So such type of symmetry we call it as cylindrical symmetry. So that is a very important point, that is the magnetic field due to a straight current carrying wire has got cylindrical symmetry. The magnetic field is cylindrically symmetric. Now, the second point, that means the magnetic field direction is always along the tangent to that loop, because the magnetic field lines are always forming concentric circles with the center lying on the wire. So that direction, it is important. And another point which we need to find, or which we need to consider is, even though the wire is infinite, the field due to this wire or the current at a finite distance is not infinite. We are getting a finite value. Okay, even if the wire is infinite, the field due to that wire at any particular point is finite. And as I said, the field is directly proportional to current and inversely proportional to the distance. And the rule to find the direction of magnetic field, we already stated the field is along the loop, circular loop. Okay, but what is the direction? How will you get the direction? That is by right hand rule. So right hand rule itself we used in the case of current carrying circular loop to find magnetic field. Here also we are using right hand rule. So in the opposite way. So the thing is this, you have to hold the conductor in the direction of thumb. That means here you have a straight wire carrying current. So hold the conductor in the direction of what, thumb. Then what is the direction in which the fingers of the right hand are curled? That direction gives the direction of magnetic field. So grasp the wire in your right hand with your extended thumb pointing in the direction of current. Fingers will curl in the direction of magnetic field. So right hand rule itself can be used in either way, either form we can say. So only this much for today. Thank you.